Hey, Math 2. New lesson coming at you. We are graphing not just single linear equations, but actual systems of equations. And this is pretty much the whole reason for this first chapter is we are going to show how systems of equations can be solved three different ways: by graphing, by substitution method, and by elimination method. So graphing just means we are going to graph both of these lines and find their intersecting point to determine its solution. So I am literally just trying to piece together what's the y equals mx plus b version of these two linear equations, and then graph them using the starting point and the rise over run, the slope. So the first one's done for us. Y equals 1x plus 2. I'm just putting the 1 in front of the x. And really, if I put a 1 here, it's the same as 1 over 1. Okay? So y-axis is the vertical, x-axis is the horizontal. I'm starting at 2 units above. So plotting our first point for this one up 2, and then we're going to go up 1, right 1 from that point. So up 1, right 1. Up 1, right 1. Up 1, right 1. And I'm just going to plot as many points as I can on this grid space. Down 1, left 1. Down 1, left 1. Remember, that's an option. The opposite, down 1, left 1, also creates a 1 in front of the x, because a negative 1 divided by negative 1 is also 1. So down 1, left 1, down 1, left 1, down 1, left 1, down 1, left 1. Connect the dots. You're done with your first line. Now, 3y equals x needs to be put in the y equals mx plus b format. Otherwise, we can't really easily graph it. So just like we learned yesterday, put a 1 in front of the x, get y by itself. I'm just going to put right off the bat that there's no b value here, so I'm going to put a plus 0 if I don't see a b. Now, divide by 3 is going to be really the only algebra move that we got to do to both sides of the equation. I wouldn't subtract and I wouldn't add, because it's literally just multiplication happening here. So y equals 1/3 x plus 0 divided by anything is still 0. And that's my second equation. So this one starts right on the origin. And then you would plot up 1, right 3. Up 1, right 3 units, as many times as you can. Up 1, right 3. Or down 1, left 3. Okay. Connect your dots. And we've found the place where the two lines intersect. It's right here. So what I'm asking you guys to do, and there's a little box below this that has a box for solution. You're going to put in the solution box, which again, I can't scroll the grid down just yet. I'm going to put the ordered pair where they intersect. So this is the ordered pair where the two lines intersect. Where they, I'm just going to say meet. So remember, ordered pairs are written as the x-coordinate first, followed by the y-coordinate second. It kind of feels reversed from rise over run. Rise is y, run is x. So you got to really manage that in your mind. XY means I go left 3 for my x-coordinate, and I go down 1 for my y-coordinate. And they're written as an ordered pair, not as a fraction, as an ordered pair. Okay? So there's also something that I talked about with this lesson called inconsistent versus consistent solutions. So negative 3, negative 1 is what goes in this box here. Consistent systems. Oh, you know what? I'm going to hold off on that. I'm going to solve all 4 of my notes examples, and then I'll go back and talk about consistent versus inconsistent. Okay? I think that'll actually work out a lot better. Number 2. We're coming back to you. All right, so again, this would be a great one to just pause and try on your own. You just get y by itself for both of them, plot the points, graph the line. All right, you paused it, you tried it on your own. Let's see if you're correct. So 2x plus 3y equals 12. I'm going to subtract the 2x from both sides because, again, I'm trying to make it look like this. I need the x's to move to the right-hand side. Flip them around, call this negative 2x plus 12. Divide both sides by 3. Everybody gets divided by 3, and you're left with negative 2/3 x plus 4. There's my first line. It means I'm going to start at 4 on the y-axis, and then I'm going to travel down to right 3. That's my rise over run. Down to right 3. Or I can go up to left 3. For my other equation, I got 2x minus y equals 4. Hey, I actually got should I show this method? I don't want to confuse you guys, so I'm not going to show that way. I'm just going to put a 1 in front of the y and do it like normal. Okay? Negative 2x on both sides. So you got negative 2x plus 4. And then don't forget to divide by that negative 1 that I created. That's going to change this to a positive 2x and this to a negative 4. So there's my second equation. I'm starting now 4 units below the x-axis. And I'm going up to right 1. So up 2, right 1, up 2, right 1, up 2, right 1. And I'm just going to plot as many points as I can. Down to left 1 works as well. And then my solution would be the point where they two. Wow. My solution would be the point at which the two lines intersect. So you go x 3, y 2, 3 comma 2. All right, these are the basic examples. On the next part of this, I'm going to show you some special cases that show up that we need to deal with. So there's nothing really special about the starting point of all this. I still got to get y by itself. So maybe just try that on your own. Pause the video because I'm going to work through it kind of quickly. All right. So I put a 0 there in place of the no b. Divide by 5, divide by 5, divide by 5. Y equals 4/5 x plus 0. That means it starts at 0, goes up 4, right 5. 1, 2, 3, 4 over 1, 2, 3, 4, 5. Down 4, left 5 also works. If I do the same thing by getting y by itself over here, again, pause it if you want to try it on your own, and then unpause it. Minus 8x from both sides because it's positive, then divide by negative 10. Now, I can reduce this fraction. If you want a shortcut, just plug it into your calculator and it'll probably reduce it for you. This turns out to be a positive, negative over negative, 4/5 x. That's what negative 8 divided by negative 10 reduces to. All right, and this is going to be minus 2 because 10 goes into 20 twice. Yeah, and then a positive divided by a negative creates a negative. This means it starts at negative 2 and then goes up 4, right 5. Down 1, 2, 3, 4, left 1, 2, 3, 4, 5. Now, an interesting thing happens. These two lines are what are considered parallel lines because they have identical slopes. Okay? So you might just want to write here on the grid, parallel lines never meet, and one way in which you can identify them before even graphing is they have the same slope. The same rise over run, slope, m value, whatever, however you want to deal with that. So they don't actually intersect. If there's no intersection, then there's no solution to speak of. So we would just write no solution right there. All right. Last example, then I'll go through and talk about consistent versus inconsistent systems of equations. The good news is they all look like they have the same starting point in terms of you got to get y by itself and plot the points. So I think everybody can do that. And then we're just talking about where they intersect. Looking good so far. All right, so the first line, done for us. I got my y-intercept, which is the b, the negative 3. Right? We're doing this. The b is negative 3 on my y-axis. The m is going to be negative 2. Now, keep in mind that negative 2x minus 3, that's the same as negative 2x over positive 1. So I'm going down to right 1, not down to left 1, down to right 1. Okay? Down to right 1, or up to left 1. Okay. Now, for the second line, I got to get y by itself. Again, pause the video, try it on your own, see if you're doing this pretty well without just watching me do it. And then we'll check our work now. Divide by 3, divide by 3, divide by 3. I already subtracted the 6x over. And you get negative 2x minus 3. Now here's the interesting part of that. It's the same equation, which means it's the same line. So all the points on this line match all the points on that line. They're basically an overlapping line. Two lines that are the same. So when you start asking, where do they intersect, which is the solution part right here, where do they intersect? Well, they intersect here, and here, and here, and here. Everywhere where they overlap. They intersect here, and here, and here. So, if I'm talking about two lines that intersect at every single point, I'm not talking about this point, and I'm not talking about that point. I'm talking about all the points on this line. So there's a couple different ways to express that. You could say all points on the line, and then actually put the line, y equals negative 2x minus 3. That's kind of a wordy explanation. Some people like to defer to this explanation. They just say, hey, there's infinitely many solutions. There's infinitely many places where these two lines intersect. So, you know what? I might go with this right here, but definitely know that all points on the line is a way to express that solution. All right, guys. Sorry, a little typo here. Copy and paste. I'm going to go now and talk about what it means to be consistent versus inconsistent. And then at the end, there's something about dependent versus independent systems. I know, it's kind of wordy. So maybe off to the side, let's put this. And you know what? I'm going to try to be brief on that because I know my video's already hitting almost 16 minutes. All right. All right, consistent systems. Very basic definition. They have at least one solution. Inconsistent systems have no solutions. That's it. So if you want to scroll back up to the first couple examples. The point of intersection here was -3, -1. Would you say that this system is consistent or inconsistent? It's consistent because it has one solution. That is at least one. It's consistent. Let's check number 2. Oh boy, what was the solution to this one? I think it was 1 point, right? 3, 2. Where they intersected. So 3, 2. That is one solution. Therefore, it is consistent. Number 3, there were no solutions because they were parallel lines. If it's no solution, then we would say it is inconsistent. And then this tends to be the one that's very difficult for students to really get nailed down. What happens if the solution is there are infinitely many solutions? What if all points on the line are solutions? Well, we got to just look at the definition here. What does it mean to be at least one solution? To be at least one solution means that this is more than one solution. That's what at least one means. It means greater than or equal to one solution. So we would say yes, if it's one line that overlaps forever, that's also consistent. All right, now lastly, very last thing. I know there's a lot going on here. There's something called a dependent system versus an independent system. When you're talking about a pair of consistent lines, when we're talking about consistent solutions, you can either be dependent or independent. So independent systems have one solution. Dependent systems have infinitely many solutions? So basically, it's just a category to place. It's a category to place where do we only intersect at one point, which was examples number 1 and 2. So examples 1 and 2 are both independent systems. Example 3 is neither, because it didn't have a solution at all. And then the last one would be categorized, number 4, as a dependent system. All right. Wow, that was a lot of information packed into 21 minutes. I hope it was helpful. Please let me know in class if you have any questions. That's all.